Okay, so let's do a couple videos about balancing redox reactions. The first video will do the acidic example and get sort of our bearings, what are we looking at, the general comments out of the way. And then in the second one we'll finish off with this basic example. So first thing I want to say is redox reactions, when you're balancing them, they're just different. If this was given to you to balance sort of in your normal procedure, well, notice one of the problems here. The problem I see is the fact that you got oxygen here, but there's no oxygens on this side. And the question mark is, well, what do you do with that? Well, what you do is you do this. You develop a procedure that can feel kind of long-winded and it's very structural. You have to follow through these steps, as they're given for it to work well. But they work, okay? These two procedures, and notice we have one dealing with a basic or acidic solution, and the other one is a basic solution. And let's just think for a second. When I say an acidic solution, I'm talking about a solution that has protons and water in it. And when I'm talking about a basic solution, it's going to be hydroxides and water. We use these compounds and these rules to balance these reactions. For example, and you'll see this early on in the, well, actually not early on, but you'll see it in the example when we actually work this example. What we'll wind up doing to balance out these oxygens, we'll put 4 water molecules over here because 4 water molecules would have 4 oxygen atoms, etc., etc. This is what the procedure is laying out. Now, before jumping into one of these, there's actually some terms that I want to remind you. I want to talk about oxidation numbers, stuff like that. And I want to do a reaction that's already balanced. It's real simple. It's one of the simplest types of redox reactions that you can come across. And what I want to do here is, well, let's look at that first step in both of these. It says split the equation into the half reactions. And what are the half reactions? Well, the half reactions are the recognition that, well, something is going to lose electrons. In this case, it's going to be the zinc. And then the other thing is going to gain electrons, which in this case is going to be the copper 2 ion. Electron transfer, that's what redox reactions are all about. And this would be the 2 half reactions that I'm talking about. Notice I'm using electrons here to balance out the charge. That's a really common theme through all redox reactions. -2 plus 2 equals 0. That equals 0 charge over here. You can almost think of these little half reactions as, a world unto themselves, if you will. You treat them as a little unit. And then at the end, when we actually balance one of these things, then we bring them together to do the overall reaction. Okay, fine. A few more terms here. And these are kind of my own sort of setup for this. Abbreviations. Right? So LEO, loss of electrons, oxidation, and half reaction. And this one's gaining reaction, or gaining the electron, so it's not the it's the GER. Let's take care of that. So this is the reduction half reaction. Let's do one more thing, at least one more thing, with this. And it's the oxidation numbers. So you need to know your oxidation rules for these types of problems. Very useful. Elemental forms, always going to have a 0 oxidation state. Monoatomic ions, oxidation state just represents the charge on the monoatomic ion. So it's going from 0 to +2. It's increasing. We can say the oxidation number is increasing, right? That's what we're observing. Well, what that means is it's this one that is oxidized. Consistent with that, right? This compound which is oxidized is the reducing agent. This oxidation process is driving the reduction process. You're only going to get a redox reaction occurring if you have two willing partners. One thing that's willing to get rid of the electrons and the other one that's willing to accept the electrons. So the fact that, you can think of it this way, the fact that this thing is pushing electrons off, in some ways it's forcing copper to take the electrons in its reduction reaction. Let's look at the values over here. Again, this is a really simple one, so I can sort of go through it very rapidly. I'm going from +2 to 0. Well, my oxidation number is being reduced, right? The verb here corresponds to physically what's happening. It's a reduction half reaction. And that which is reduced is the oxidizing agent. So just a few reminders here about these terms. And then I know in class we went through oxidation numbers just as an exercise, and now we're actually applying it to understand a reaction as it's taking place. That's enough for that one. Let's actually go through one of these. We're going to do this first one in an acidic solution. And let me just quickly do an overview here. And we're going to split the half reactions, and then we're going to take care of hydrogens and oxygens. Let me make some notations here on the side. So let's do just a quick overview here. And the first thing we're going to balance are all the atoms except for hydrogens and oxygens. In some cases, you skip this. If there's nothing but hydrogen and oxygen, you don't worry about it. Or if everything's already balanced, you don't have to worry about it. We actually see that in the first example. And then to each half reaction, remember I was saying that a half reaction is sort of its own little thing that you have to deal with. And then secondly, that's where we're going to balance the O's and the H's. In that order, we're going to balance oxygens first in this step, and then the hydrogens second. After we get to this point, so, steps, by the time we get through steps 2 and 3, the atoms are balanced. That's an important point, actually. Then, and I'm going to change gears just a little bit, different color. This here, use only electrons to balance charge. Very important. I mean, all of this is important, but that's especially important. And again, you do that to each half reaction. Step 5, we're going to compare both half reactions and make sure, like in this example, make sure that we have equal numbers. Notice we had 2 being kicked off here. We have 2 being accepted there. That's step number 5 here, is adjusting the electron numbers if you need to, so that the 2 half reactions do just this. However many are kicked off, or the exact number that gets accepted by the reduction half reaction. And then in the last step, we'll combine the 2 half reactions together. So let's start with this one. Let's see what it looks like. And sometimes the half reactions are very quick, sometimes they're not. For example, I can do this one pretty easily. Okay, I already know what this looks like. I know that I need 2 electrons there. And then this is the Leo half reaction. That half reaction is done. I like that. Let me just stop for a minute and think about the rules that are written on that little cheat sheet, which I would encourage you to have out, because I'm not necessarily going to jump back. Like right now, I'm not going to jump back to it. But in that procedure, what it says is balance the atoms except for hydrogen and oxygen. Okay, zinc is balanced already on both sides. And then it says take care of oxygens and hydrogens. Well, there are no oxygens and hydrogens in this half reaction, right? The half reaction is its own little thing that you would treat separate from the other half reaction. It's the other half reaction that you got to deal with, the hydrogen and oxygens. Okay, that's fine. Now, since all the atoms are balanced, right, zinc, one zinc, then you use only electrons to balance the charge. And, you know, what I'm doing here, I have an overall charge of 0 here and an overall charge of 0 there. Overall charge. Sometimes it's 0 and 0, sometimes it's 2 and 2, sometimes it's -3 and -3. It just depends. What you're doing is you're using electrons to balance the charges out. As long as it's the same charge on either side, that's what you want. And in this case, since this side had 0 and this side had -2 before adding the electrons, the only way I could balance the charge using electrons was to add 2 on this side, so it canceled out the +2 charge there. If I had added +2 over here, then it would have been a total -2 +2. You can't go that route. It doesn't work. This is done for right now. Okay, let's focus on our other half. So like I said, and I know this one's done, so I'm going to a lot of times when you do these exercises, it's going to take up a lot of space on the page. And so usually if I'm practicing, I still practice occasionally with these things, usually I get scrap paper and have a lot of space to work with. Okay, first step in the instruction. Now, right, we're gonna go through. Right, we're gonna go through this entire sequence, at least up through what? We're gonna go through 2 to 4 for this particular half reaction. Let's do that. So the first thing, all the atoms except for hydrogen and oxygen, so the sulfur. Right, that's good. I got one. I have one sulfur on this side, one sulfur on that side. I don't have to do anything. Next topic. Next thing is what I want to do, right? Oh yeah, let's make some little notes here. To balance out the oxygens, we're going to use water. To balance out the hydrogens, we're going to use protons. In an acidic solution, you have water and you have protons. That's the only two things you have to work with. And so here, if I have 4 oxygen atoms here, then I need, how many water molecules are going to contain or give me 4 oxygen atoms? Well, that's 4 water molecules. Right? There's 1 oxygen per molecule. I need 4 of them. Oxygens are balanced. Now, what about the electron count? Well, the electron, or not the electron count, the proton count, the hydrogen count. On this side I got 2, I have 8, I have 10. I have 10 H's on this side. Let's highlight. And if I look on my reactant side, I have 2 already listed, so that means I need to add 8 protons. So don't be intimidated by these large numbers. Usually when you're balancing like metathesis reactions that we've dealt with before, or the reactions that you saw in Gen Chem 1, rarely did you get to 10, 8, 28. Sometimes these numbers get really large, and just go through the sequence. And at the end of the procedure, if it doesn't add up, then you got to go back and check. But again, don't worry so much about these numbers of these large numbers that you might be generating. I've applied the rules correctly so far, and then yeah, all the atoms are balanced. Now I need to balance out the electrons. So let's different color. No, let's not. Let's just go back to the blue. Now, one thing to note: we're talking about a redox reaction, electron transfer. If we have an oxidation reaction here, this part better be the reduction reaction. There's a couple of internal checks that you can observe as you're doing these to know that you're on the right track anyway. And so far we're on the right track, I think, because if we look at the overall charge here, there's an overall charge of 0, on this side, and there is a +8 charge over here. So what that's going to require is that I put in 8 electrons on the reactant side. It's accepting the electron, so it is a reduction reaction. There's my first internal check. That's good. And this half reaction is balanced both in atoms and charge, and that's your goal for any kind of balancing act, whether it's a half reaction or an overall reaction. So now let's take a look at this example. And one thing that we need to observe here is the fact that the number of electrons that are being transferred is not equal. For every half reaction as written here, I'm only kicking off 2 electrons. For this half reaction, I need 8 electrons. Well, what you have to do is you have to adjust the number of electrons so that that transfer is equal amount. This is getting back to right here, step 5 here. In step 5, that's where you're getting that little comment. Balance the number of electrons and add up the half reaction. So balancing the number of electrons is what I did right here. Let me carry that 4 all the way through. So 2 times 4, I have 8 electrons now. And then I'll have 4 zinc cations, and I'll have 4 zinc atoms. I'm going to go ahead and scribble that out just so it reminds me that I have done that. And now I'm ready to add everything up. Now when I say add everything up, well, one thing to note is that the electrons are going to cancel out for us. So if you think about, the little reaction arrow as our dividing line, any common compound or atom or electron in this case that's on this side and that side can be canceled out. Now in this particular example, it's only the 8 electrons. So in a future example, you'll see a little bit more work here. And really now I'm ready to add up these 2 half reactions to get my overall balanced molecular equation is basically what we're shooting for. It doesn't matter which order you place these in. I'm just usually what I do is, whatever's in the overall or whatever's in the reaction is given, those 2 things come first. And then the hydrogens and waters and all that will come second. So I'm going to try to stick with that pattern. I got that, and then this is the only thing left. So I got 8 protons. Same thing over here. I need 4 zinc cations. And I need to bring in the hydrogen sulfide, and now 4 water molecules. And that is my balance equation. If I went in and counted everything up, it should be fine. There's 10 hydrogens on this side. There's 10 hydrogens on this side. 4 zinc, 4 zinc, 4 oxygens, 4 oxygens. Everything's balanced. Charges are balanced. They should be 4 times 2 plus 8 here. Everything's balanced. Right? As long as the charges and the atoms are balanced for a reaction, you're done basically. Now, I guess there would also be, let's just go ahead and add all these tags. They're not shown here, so you wouldn't necessarily have to put them in. This is probably kicking off as a gas, G, and then liquid there. And then that's it in terms of balancing the reaction. And I'm going to make a notation. Let's see. The oxidation reaction that's taking place. That means that zinc is the reducing agent. Right? That which is oxidized is the reducing agent, and then that which is reduced is the oxidizing agent. The other thing I want to do with this real quick is say that we have oxidation numbers. Let's do oxidation numbers. Up top here in green. We've already talked about the zinc. It's increasing oxidation. It's increasing oxidation numbers. It is being oxidized. That's what we observe in the half reaction. And then to double check our work here, then the sulfur here better be reducing. Why am I focusing on sulfur? Well, if you look at the oxidation rules, you know that the hydrogen always comes in at a +1 charge each time, unless there's a couple of exceptions that you look at those rules, but very unlikely to see that. Oxygen is typically coming in at a -2 oxidation number, so there's 4 times a -2, so that's a -8 oxidation charge here. The overall charge for this molecule is 0. So if the sulfur is carrying a +6 charge, then the +6 +2 cancels out the -8, 0. Right? The sum of the oxidation numbers have to add up to the overall charge of the molecule or ion, in this case 0. So the sulfur is carrying a +6 charge. This sulfur is carrying a -2. Right? Yeah, -2 charge. So that's a dramatic change. I mean, it's reducing, right? So if there's a reduction in the oxidation number, then that indicates that atom here is being reduced, and we see that in the oxidation numbers. So again, oxidation numbers is a very handy tool to keep track of how electrons are flowing in a particular example. And notice, what's the difference between +6 and -2? That's 8. Plug that on calculator. There's 8 numbers between those two. Well, that just happens to correspond to the 8 electrons that are being transferred. Remember, oxidation number, that's just a bookkeeping tool to keep track of electron flow. And that's enough. This is a long video, and all reactions, if you get a redox reaction and it says acidic, it's these sequences that you're running through over and over again. And stick with this list pretty closely. If you deviate from this list, you'll probably get it wrong. So just a heads up for you. This is good practice, just having this out every time you're doing one of these things early on. You'll need to know these for the test, by the way. So you will not have this little cheat sheet for the test. Okay, and there'll be a second one for the basic reaction.